Hi everyone, today we'll be taking a look at a question on complex number. So in this question, two of the roots of the equation are given by 1 plus 4i and minus 2. Find the values of a and b and the remaining roots of the equation. So since we know that 1 plus 4i is a root, so we can just substitute 1 plus 4i into this expression. So we get a 1 plus 4i to the power of 4 minus 1 plus 4i cubed plus 26 1 plus 4i square plus b 1 plus 4i minus 34 equal to 0. We can evaluate these terms by using our graphical calculator, and by expanding and arranging, we will be able to get 161a plus b minus 377 plus I 240a minus 4b minus 260 equal to 0. By comparing the real part and the imaginary part, we can see that this term here is equal to 0, this term here is also equal to 0. So we will be able to extract out two equations. So we get 161a plus b equal to 377. We call it equation 1. The other equation we'll get is 240a minus 4b equal to 260, equation 2. Using our GC to solve this simultaneous equation, we will be able to get a equal to 2, b equal to 55. Therefore, our final expression will be 2z to the power of 4 minus z cubed plus 26z squared plus 55z minus 34 equal to 0. And using our graphical calculator once again, we will be able to find the remaining roots of this equation. So by using our calculator, we will get z equal to 1 plus 4i, z equal to 1 minus 4i, z equal to minus 2, and z equal to half. So basically, this question is relatively straightforward, but there's a problem because it's not uncommon for the questions, right? For this type of question, they say that you are not supposed to use the calculator to solve this question. So look at this expression here. It will be very tedious and cumbersome to expand out using binomial expansion, which may be too long. So there might be an alternative method that is better. So let me just show you how do we do this. So we can first, by considering the factors of the equation. So the factors of the equation can be obtained by looking at the known roots they give you, which is simply 1 plus 4i. So we can also use use of the conjugate root theorem. We can also say that 1 minus 4i is also the root. And the other root given to us is minus 2. So we can consider these factors here, which is given by z minus 1 plus 4i, the first root, z minus 1 minus 4i, the other root, and we get z plus 2, the last root. So we need to expand out everything, and we will try to compare this equation with this equation and try to find the unknown a and b, right? But the problem here is if you want to expand out 3 terms with 3 terms, it might be a bit tedious. But there's a better way of doing that. That is by using the identity of a minus b, a plus b equal to a squared minus b squared. So here we will try to regroup it into a real part and imaginary part, which is z minus 1 minus 4i, z minus 1 plus 4i, z plus 2. So we can look at this like a, this is the b, this is the a, this is the b. So by expanding this using this identity, we can see that we will get z minus 1 square minus 4i square. And expanding everything here, we'll get z square minus 2z plus 1 plus 16. Okay, and expanding everything out again, we should be able to end up with z cubed plus 13z plus 34. So the next part that we can do is by equating this equation with this equation. So we will get z cubed plus 13z plus 34. And we need to consider the last factor. So the last factor, right, by observation, we can see that since the coefficient of z to the power of 4 is a, so we can just put a z. And comparing with the constant term, we can see that it should be a minus 1 here. Then after that, what we can do is by equating coefficient of z square. By equating coefficient of z square, we can see that z square is given by 13a, which give me 26. So from here, we will be able to solve that a equal to 2. Okay, the next part, we can equate coefficient of z, which is given by, so from here, we can see coefficient of z is minus 13. Coefficient of z is 34a, which is given by b. And since a is already found, which is 2, so we can substitute a to be 2. So therefore, b will just be equal to 55. Okay, so let's take a look at part B of the question. It's given that w equal to square root 3 plus I to the power of 10. Without using a graphical calculator, find the modulus and argument of w. So we have w equal to square root 3 plus I to the power of 10. Modulus of w will just be modulus of square root 3 plus I to the power of 10. Will just give me 2 to the power of 10, which is just 1024. Argument of w is given by argument of square root 3 plus I to the power of 10. And we can actually bring down the power of 10 due to the properties of argument, which is 10 argument of square root 3 plus I. And argument of square root 3 plus I will just give me pi over 6. Simplifying, we get 5 pi over 3. But we know that 5 pi over 3 exceeds the principal range for the argument, so we need to do a minus 2 pi, which is just give me a minus pi over 3. So next part of the question says, hence find the smallest positive integer n for which w n over w conjugate is real. So we need to find wn over w conjugate is real. This is a very kind of popular type of question. So usually what I will do, right, I have a template for doing this type of question. It's like purely real, purely imaginary. So for purely real, I will set the argument to be k pi. And for purely imaginary, I will set the argument to be k pi plus pi over 2. So in this situation, I need to determine what is the argument of this one. So the argument of wn over w conjugate is given by argument of wn minus argument of w conjugate. This is a properties of complex number. And we can also see that we can bring down the power here. So we get n argument of w. And argument of w conjugate is negative of argument of w, which is just plus argument of w. Simplifying, we get n plus 1 argument of w. Right. Since this question wants us to say that it is purely real, so purely real, I will equate this particular term with k pi. And since from the previous part, we already know that the argument of w is equal to minus pi over 3, so we can just simply substitute inside here. So we get n plus 1 minus pi over 3 equal to k pi. And by rearranging this, we will be able to get n equal to minus 3k minus 1, where k is an element of positive, k is an element of integers. So we can actually, what we can do, right, is to sum in a first few values of k, some values of negative, some values of positive, to see which are the values of n that give me the least value. So by substituting k equal to minus 2, I will get n equal to 5. When I sub k equal to minus 1, I get n equal to 2. And when I try to sub k equal to 0, I'll get n equal to minus 1. So by trying our first few values, we will know that our required values of n is this. So therefore, this n is just equal to